Hello everyone, this is an audio lecture for visually impaired students on thermochemistry from the book Atkins Physical Chemistry. The study of the energy transferred as heat during the course of chemical reactions is called thermochemistry. Thermochemistry is a branch of thermodynamics because the reaction vessel and its contents from a system and chemical reactions result in the exchange of energy between the system and the surroundings. Calorimetry can be used to measure the energy supplied or discarded as heat by a reaction, with Q identified with the change in internal energy if the reaction occurs at constant volume, or with the change in enthalpy if the reaction occurs at constant pressure. Conversely, if delta U or delta H for a reaction is known, it is possible to predict the heat the reaction can produce. As pointed out in topic 2a, a process that releases energy as heat is classified as exothermic, and one that absorbs energy as heat is classified as endothermic, because the release of heat into the surroundings at constant pressure signifies a decrease in the enthalpy of a system. It follows that an exothermic process is one for which delta H is less than 0. Such a process is exenthalpic. Conversely, because the absorption of heat from the surroundings results in an increase in enthalpy, an endothermic process has delta H greater than 0. Such a process is endenthalpic. Exothermic process delta H is less than 0. Endothermic process delta H is greater than 0. Standard enthalpy changes. Changes in enthalpy are normally reported for processes taking place under a set of standard conditions. The standard enthalpy change delta H naught is the change in enthalpy for a process in which the initial and final substances are in their standard states. The standard state of a substance at a specified temperature is its pure form at 1 bar. For example, the standard state of liquid ethanol at 298 Kelvin is pure liquid ethanol at 298 Kelvin and 1 bar. The standard state of solid iron at 500 Kelvin is pure iron at 500 Kelvin and 1 bar. The definition of standard state is more sophisticated for solutions. The standard enthalpy change for a reaction or a physical process is the difference in enthalpy between the products in their standard states and the reactants in their standard states, all at the same specified temperature. An example of a standard enthalpy change is the standard enthalpy of vaporization, delta H vaporization naught, which is the enthalpy change per mole of molecules when a pure liquid at 1 bar vaporizes to a gas at 1 bar, as in H2O liquid changes to H2O gas, and enthalpy of vaporization at 373 Kelvin is plus 40.66 kJ per mole. As implied by the examples, standard enthalpies may be reported for any temperature. However, the conventional temperature for reporting thermodynamic data is 298.15 Kelvin, unless otherwise mentioned or indicated by attaching the temperature to delta H naught. All thermodynamic data in this text are for this conventional temperature. The attachment of the name of the transition to the symbol delta, as in delta H vaporization, is the current convention. However, the older convention is delta H vaporization is still widely used. The current convention is more logical because the subscript identifies the types of chains, not the physical observable related to the chains. Enthalpies of physical chains. The standard molar enthalpy change that accompanies a change of physical state is called the standard enthalpy of transition and is denoted by delta T or H naught. The standard enthalpy of vaporization is one example. Another is the standard enthalpy of fusion, delta H naught fusion. The standard molar enthalpy change accompanying the conversion of a solid to a liquid as in H2O solid changes into H2O liquid and enthalpy of fusion at 273 Kelvin is plus 6.01 kilojoule per mole. As in this case, it is sometimes convenient to know the standard molar enthalpy change at the transition temperature as well as at the conventional temperature of 298 Kelvin. The different types of enthalpy changes encountered in thermochemistry are summarized in table 2c.2. Because enthalpy is a state function, a change in enthalpy is independent of the path between the two states. This feature is of great importance in thermochemistry because it implies that the same value of delta H naught will be obtained however the change is brought about between specified initial and final states. For example, the conversion of a solid to a vapor can be pictured either as occurring by sublimation, the direct conversion from solid to vapor, H2O solid changes into H2O gas, or as occurring in two steps. First fusion, that is melting, and then vaporization of the resulting liquid. H2O solid changes into H2O liquid, enthalpy of fusion, and H2O liquid changes into H2O gas, standard enthalpy of vaporization. Overall, H2O solid changes into H2O gas is equal to standard enthalpy of fusion plus standard enthalpy of vaporization. Because the overall result of the indirect path is the same that of the direct path, the overall enthalpy change is the same in each case, and for processes occurring at the same temperature. So, standard enthalpy of sublimation is equal to standard enthalpy of fusion plus standard enthalpy of vaporization. It follows that because all enthalpies of fusion are positive, the enthalpy of sublimation of a substance is greater than its enthalpy of vaporization at a given temperature. Another consequence of H being a state function is that the standard enthalpy change of a forward process is the negative of its reverse. For instance, because the enthalpy of vaporization of water is plus 44 kJ per mole at 298 Kelvin, the enthalpy of condensation of water vapor at the temperature is minus 44 kJ per mole. Enthalpies of chemical change. There are two ways of reporting the change in enthalpy that accompanies a chemical reaction. One is to write the thermochemical equation, a combination of a chemical equation and the corresponding change in standard enthalpy. CH4 gas plus 2O2 gas changes into CO2 gas plus 2H2O gas. And standard enthalpy change is minus 890 kilojoule. Now, delta H naught is the change in enthalpy when reactants in their standard states change to product in their standard states. Pure separate reactants in their standard states changes into pure separate products in their standard states. Except in the case of ionic reactions in the solution, The enthalpy changes accompanying mixing and separation are insignificant in comparison with the contribution from the reaction itself. For the combustion of methane, the standard value refers to the reaction in which 1 mole CH4 in the form of pure methane gas at 1 bar reacts completely with 2 mole O2 in the form of pure oxygen gas to produce 1 mole CO2 as pure carbon dioxide at 1 bar and 2 mole H2O as pure liquid water at 1 bar. The numerical value quoted is for the reaction at 298.15 Kelvin. Alternatively, the chemical equation is written and the standard reaction enthalpy delta H naught or standard enthalpy of reaction reported. Thus, for the combustion of methane at 298 Kelvin, write CH4 gas plus 2O2 gas changes into CO2 gas plus 2H2O gas and standard enthalpy of reaction is equal to minus 890 kJ per mole. For a reaction of the form 2A plus B changes into 3C plus D, the standard reaction enthalpy would be delta HR naught is equal to 3 del HM naught C plus HM naught D minus 2 HM naught A plus HM naught B, where HM naught J is the standard molar enthalpy of species J at the temperature of interest. Note how the per mole of delta R H naught comes directly from the fact that molar enthalpies appear in this expression. The per mole is interpreted by noting the stoichiometric coefficients in the chemical equation. In this case, per mole in delta HR naught means per 2 mole A, per mole B, per 3 mole C, or per mole D. In general, delta HR naught is equal to, where in each case the molar enthalpies of the species are multiplied by their dimensionless and positive stoichiometric coefficients V. This formal definition is of little practical value. However, because the absolute values of the standard molar enthalpies are unknown, this problem is overcome by following the techniques of section 2C2A. Some standard reaction enthalpies have special names and significance. For instance, the standard enthalpy of combustion delta Hc naught is the standard reaction enthalpy for the complete oxidation of an organic compound to CO2 gas and liquid H2O if the compound contains C, H and O, and to N2 gas if N is also present. Hess law. Standard reaction enthalpies can be combined to obtain the value for another reaction. This application of the first law is called Hess law. The standard reaction enthalpy is the sum of the values for the individual reactions into which the overall reaction may be divided. The individual steps need not be realizable in practice. They may be hypothetical reactions, the only requirement being that their chemical equations should balance. The thermodynamic basis of the law is the path independence of the value of delta H R naught. The importance of Hess law is that information about a reaction of interest, which may be difficult to determine directly, can be assembled from information on other reactions. Example 2C1. Using Hess law, the standard reaction enthalpy for the hydrogenation of propene CH2 double bond CH CH3 gas plus H2 gas changes into CH3 CH2 CH3 gas is minus 124 kilojoule per mole. The standard reaction enthalpy for the combustion of propane CH3 CH2 CH3 gas plus 5O2 gas changes into 3CO2 gas plus 4H2O liquid is minus 2 1220 kilojoule per mole. The standard reaction enthalpy for the formation of water H2 gas plus half O2 gas changes into H2O liquid is minus 286 kilojoule per mole. Calculate the standard enthalpy of combustion of propane. The skill you need to develop is the ability to assemble a given thermochemical equation from others. Add or subtract the reactions given together with any others needed so as to reproduce the reaction required. Then add or subtract the reaction enthalpies in the same way. Solution. The combustion reaction is C3H6 gas plus 9 by 2 O2 gas changes into 3CO2 gas plus 3H2O liquid. The reaction can be repeated from the following sum. C3H6 gas plus H2 gas changes into C3H8 gas. C3H8 gas plus 5O2 gas changes into 3CO2 gas plus 4H2O liquid. H2O liquid changes into H2 gas plus half O2 gas. Standard enthalpies of formation. The standard enthalpy of formation delta HF naught of a substance is the standard reaction enthalpy for the formation of the from its elements in their reference states. The reference state of an element is its most stable state at the specified temperature and 1 bar. For example, at 298 Kelvin, the reference state of nitrogen is a gas of N2 molecules. That of mercury is liquid mercury. That of carbon is graphite. And that of tin is the white metallic form. There is one exception to this general prescription of reference state. The reference state of phosphorus is taken to be white phosphorus, despite this allotrope not being the most stable form, but simply the most reproducible form of the element. Standard enthalpies of formation are expressed as enthalpies per mole of molecules or formula units of the compound. The standard enthalpy of formation of liquid benzene at 298 Kelvin, for example, refers to the reaction 6 carbon solid graphite plus 3H2 gas changes into C6H6 liquid and is plus 49 kilojoule per mole. The standard enthalpies of formation of elements in their reference states are zero at all temperatures because they are enthalpies of such null reactions as N2 gas changes into N2 gas. Some enthalpies of formation are listed in tables 2C.4 and 2C.5 and a much longer list will be found in the resource section. The standard enthalpy of formation of ions in solution poses a special problem because it is not possible to prepare a solution of either cations or anions alone. This problem is overcome by defining one ion conventionally, the hydrogen ion, to have zero standard enthalpy of formation at all temperatures. Conceptually, a reaction can be regarded as proceeding by decomposing the reactants into their elements in their reference states and then forming those elements into the products. The value of delta HR naught for the overall reaction is the sum of these unforming and forming enthalpies, because unforming is the reverse of forming. The enthalpy of an unforming state is the negative of the enthalpy of formation. Hence, in the enthalpies of formation of substances, there is enough information to calculate the enthalpy of any reaction by using delta HR naught is equal to sum of enthalpy of formation of products multiplied by their coefficients minus sum of enthalpy of formation of reactants multiplied by their coefficients, where in each case the enthalpies of formation of the species that occur are multiplied by their stoichiometric coefficients. This procedure is the practical implementation of the formal definition in equation 2c3. A more sophisticated way of expressing the same result is to introduce the stoichiometric numbers Vj as distinct from the stoichiometric coefficients, which are positive for products and negative for reactants. Stoichiometric numbers which have a sign are denoted by J or Vj. Stoichiometric coefficients which are all positive are denoted simply V with no subscript. The temperature dependence of reaction enthalpies. Many standard reaction enthalpies have been measured at different temperatures. However, in the absence of this information, standard reaction enthalpies at different temperatures can be calculated from heat capacities and the reaction enthalpy at some other temperature. In many cases, heat capacity data are more accurate than reaction enthalpies. Therefore, providing the information is available, the procedure about to be described is more accurate than the direct measurement of a reaction enthalpy at an elevated temperature. It follows from equation 2b.6a dH is equal to C subscript P dt that when a substance is heated from T1 to T2, its enthalpy changes from HT1 to HT2 and HT2 is equal to HT1 plus integration of C P dt from T1 to T2. It has been assumed that no phase transition takes place in the temperature range of interest because this equation applies to each substance in the reaction. The standard reaction enthalpy changes from delta H naught R T1 to delta H naught R T2 is equal to delta H naught R T1 plus delta R Cp naught dt integration T1 from T where delta Cp naught R is the difference of the molar heat capacities of products and reactants under standard conditions weighted by the stoichiometric coefficients that appear in the chemical equation or in the notation of equation 2c.5p. Equation 2c.7a is known as Kirchhoff's law. It is normally a good approximation to assume that delta Cp R naught is independent of the temperature, at least over reasonably limited ranges. Although the individual heat capacities might vary, their difference varies less significantly. In some cases, the temperature dependence of heat capacities is taken into account by using equation 2c.7a. If delta Cp R naught is largely independent of temperature in the range T1 to T2, the integral equation 2c.7a evaluates to T2 minus T1 delta Cp R naught, and that equation becomes delta H R naught T2 is equal to delta H R naught T1 plus delta Cp R naught T2 minus T1. Differential scanning calorimetry. A differential scanning calorimeter DSC measures the energy transferred as heat to or from a sample at constant pressure during a physical or chemical change. The term differential refers to the fact that measurements on a sample are compared to those on a reference material that does not undergo a physical or chemical change during the analysis. The term scanning refers to the fact that the temperatures of the sample and reference material are increased or scanned during the analysis. A DSC consists of two small compartments that are heated electrically at a constant rate. The temperature T at time small t during a linear scan is T is equal to T naught plus alpha T, where T naught is the initial temperature and alpha is the scan rate. A computer controls the electrical power supply that maintains the same temperature in the sample remains throughout the analysis. If no physical or chemical change occurs in the sample at temperature T, the heat transferred to the sample is written as small qp is equal to Cp delta T, where delta T is equal to T minus T naught and Cp is assumed to be independent of temperature. Because T is equal to T naught plus alpha small t, it follows that delta T is equal to alpha small t. If a chemical or physical process takes place, the energy required to be transferred as heat to attain the same change in temperature of the sample as the control is Qp plus Qpex. The quantity Qpx is interpreted in terms of an apparent change in the heat capacity at constant pressure from Cp to Cp plus Cpx of the sample during the temperature scan, where P external is equal to Qp external divided by T is the excess electrical power necessary to equalize the temperature of the sample and reference compartments. A DSC trace, also called a thermogram, consists of a plot of Cp external against T. The enthalpy change associated with the process is delta H is equal to Cp external dt integrated from T1 to T2, where T1 and T2 are respectively the temperatures at which the process begins and ends. This relation shows that the enthalpy change is equal to the area under the plot of Cp external against T. P. Isothermal titration calorimetry. Isothermal titration calorimetry (ITC) is also a differential technique in which thermal behavior of a sample is compared with that of reference. The apparatus is shown in figure 2c.41 of the thermally conducting vessels, which have a volume of a few cubic centimeters, contain the reference and a heater rated at a few millivolts. The second vessel contains one of the reagents, such as a solution of a macromolecule with binding sites. It also contains a heater. At the start of the experiment, both heaters are activated and then precisely determined amounts of volume of about a cubic millimeter of the second reagent are added to the reaction cell. The power required to maintain the same temperature differential with the reference cell is monitored. If the reaction is exothermic, less power is needed. If it is endothermic, then more power must be supplied. A typical result is shown in figure 2c.5, which shows the power needed to maintain the temperature differential from the power and the length of time. Delta T, for which it is supplied, the heat supplied Qi for the injection I can be calculated from Qi is equal to Pi delta T. If the volume of solution is V and the molar concentration of unreacted reagent A is Ci at the time of the ith injection, then the change in its concentration at that injection is delta Ci, and the heat generated or absorbed by the reaction is V delta Hr. Delta Ci is equal to Qi. The sum of all such quantities, given that the sum of delta Ci is the known initial concentration of the reactant, can then be interpreted as the value of delta Hr for the reaction. Checklist of concepts. Number 1. The standard enthalpy of transition is equal to the energy transferred as heat at constant pressure in the transition under standard conditions. Number 2. The standard state of a substance at a specified temperature is its pure form at 1 bar. Number 3. A thermochemical equation is a chemical equation and its associated change in enthalpy. Number 4. Hess law states that the standard reaction enthalpy is the sum of the values for the individual reactions into which the overall reaction may be divided. Number 5. Standard enthalpies of formation are defined in terms of the reference state of elements. Number 6. The reference state of an element is its most stable state at the specified temperature and 1 bar.